All right. Welcome to part two, right, of the 2019 exam paper. Now, what I must say is that I won't complete the paper. The other question is related to X-rays, X-ray attenuation, and all of that. That is not something that is a part of the topics, right, that Cape said that they're going to give us. So I won't spend the time to do that. But one thing for sure that I'll do afterwards is a video on photoelectric effect. All right, because I know a few persons have been requesting that. So let's just finish up this particular question. So it says that figure. So the graph in figure 4 on page 13 shows the relationship between the resistance RL of a particular LDR and the light intensity I, right, lux, on its surface. It says that the equation of a line, let me say this again, yeah. So the equation of the line on the graph is this. So, ladies and gentlemen, in physics, right, you'll always see equations. I mean, that is a given, and you will always see some type of linear equation. One of the things you must be able to can easily identify. If they tell you, so let's look at the graph. Here's the graph. The graph is log of base 10 RL versus log of base 10 I. So this is your x variable, and this is your y variable. All right, simply put. Now we know that whenever we're dealing with a straight line, right? Whenever we're dealing with a straight line, there is a particular equation, right? That says y is equal to mx plus c. Now these are the things that Kip likes to ask you guys. You understand? They like to link um their equations to the straight line equation. So what we're going to do now is that we're just going to simply identify our variables. If you fail to identify your variables correctly, then chances are you're going to get the answers incorrect. So let's look at it now. Remember that the graph is log of RL versus log of what was it again? I. Yeah. So from this equation here, we can identify which is going to be my y variable, which is going to be my x variable. This is my y variable, right? Then this right here, log of base 10I, that is going to be my x variable. Now, ladies and gentlemen, we know that y is equal to mx plus c. Now, seeing that we know where x is located, automatically, whatsoever is beside x, that corresponds to your gradient. So technically speaking, m, which is your gradient, right? And that's the gradient of the straight line, is equal to negative b. Okay? Then we know, based on the y equal mx plus c, c in this case talks about the y-intercept. And that is where the line cuts the y-axis, right here. Okay? So this is our c value. So from there and then we can simply see that that is what these are the variables that we can identify based on the equation and the equation of a straight line. Now they say use the graph to determine numerical values for B and R naught. R naught is right here. So let's go to the graph right now. So we want to find the gradient, okay? Because we said that the gradient corresponds to B. Now, ladies and gentlemen, whenever you see a graph going down like this, you can easily know that the gradient is going to be negative. Right? Whenever you have the line going on like this, that's going to be it's going to give you a negative gradient. It's just like going on a hill, it's a negative gradient. If the line is going up in the air, that's a positive gradient. So we have identified some things now already. What we're going to do is just calculate the gradient. We know gradient, the formula for gradient is equal to y2 minus y1 divided by x2 minus x1. Now, I'm going to pick my first point here. So I go ahead and indicate on my graph which points I'm picking. Yeah, I can think I can use that. And then I use that one. So this is my x1, my y1. This is my x2, my y2. So let's see now. So the y2 value in this case is going to be 1.5 minus the y1 value is going to be 4.5. Then I divide that now by x2. X2 is 3.5. All right. Yeah, let me just, yeah. Okay, okay. All right, let me just correct something here. So this is 0 0.5 rather. So that first x, what am I doing? Let me just go back here and check what's happening here. I Let me just check. All right. So the y2 value, right? The y2 value is going to be I think I had it correct. Yeah, 1.5, right? Then no, the y1 no is going to be 4.5. Divide that now by the x2. X2 is going to be 3.5 minus x1. That's going to equal to 0.5. So that's the correct thing. So you can go ahead now and put it in your calculators, right? So we have 1.5 minus 4.5. We get -3, okay? And then now we're dividing that now by, when we subtract this, we get 3. So m, right, is equal to -3 divided by 3, right? So at the end of the day, we can see now that m is equal to -1. Now, ladies and gentlemen, remember a while ago around here, so we said that m is equal to -b, right? So it now means that uh, because m now is equal to 1, right? And that is equal to -b, negative and negative cancel out, which means that b is equal to 1, okay? So that's how we find b. Now, they want us to find r naught. They want us to find r naught. So to find r naught, we clearly look on the graph and see where the line cuts the y-axis, right? So that this is our y-intercept. Intercept. I don't know if I'm saying it correctly. Intercept. Right? So our y-intercept is right here. So basically, uh, c is equal to we know c is equal to log of base 10 times r naught. The value for c in this case is 5. So 5 is equal to log of base 10 times r naught. Now, there are some rules governing the laws of log. So if I want to find r naught, right, then I would have to find the antilog, right? The antilog of 5 to give me what r naught is equal to, which is the same thing as saying base 10 raised to the power 5. Now, if you want to find the antilog on your calculator, right, it is simple. All you need to do is to press shift and press log, and then press 5, and that's going to give you the antilog. But, for the mathematicians, they can easily identify when you can, use the whole base 10 raised to the power 5 and all that kind of stuff, right? There are some rules governing logs that, I mean, it is, you know, how can I say? So imagine that we have log of b, raised to the power a equals c. If I want to I wonder if this is how it was structured. All right, I don't want to go into that, but there's something related to this that I need to review it for myself as it pertains to that, right? As it pertains to this, I need to review that. But for this scenario though, once you can find the anti-log, and I that's the easiest way that I can remember it. So just whenever you want to find R or something over this side, you just find the anti-log. So you're basically trying to get rid of log. So to get rid of log, you have to anti-log it so that you can pretty much find this thing over here, or to find what R naught is equal to. So technically R naught, which is basically a resistance, right? So that is equal to 10 to the 5 ohms. So we find R naught, right? Now let's see what else the question dictates to us. It says using the equation given in C to determine an expression for RL in terms of R naught and I. So this is the expression that they are talking about, right? So or that equation I should say. So what they want us to do here, they want us to get a more refined equation. The trick about this, not say the trick, but they are trying to test your knowledge of doing stuff the reverse way. Because normally you would get an equation and you would have to expand it, right, using the whole logs and all of that. But no, they want you to how would I say it, to shrink it back to the original equation. So that's the trend I'm seeing here based on this question. So um, laws of logs can tell us a lot of things here. So right, it's a 1 mark question by the way. The laws of log tells us that whenever you're subtracting logs, you basically can divide it, right? So rather than having um, log of base 10 R naught minus B, but before I do that, whenever we see this thing here, like the minus B ln uh, naught I, this B or this minus B originally was supposed to be in the power, right? Just give me 1 second. So whenever we see something of this nature, let's imagine we have minus B ln uh, base 10 to the I. This B technically came from in the power. So we could rewrite it to say ln, um, ln base 10 I to the minus B. So that is technically where it is coming from. So so we could definitely replace that. So we could put a plus sign and put ln base 10 I to the minus b. Then what we could do now is factor out the log of base 10, seeing that they're constant. The laws of log tell we can say that we can do that, right? So if I can shrink this, so whenever you have a plus sign, it simply means that we are multiplying or yeah. So laws of log say we can split the thing. If you're multiplying, you can split it, right? And it becomes a plus. So if you have a plus, then we can now recombine it so that it becomes a multiplication thing per se. So we're going to factor out log of base 10, and we're going to have R naught I minus B, right? And we're obviously going to write back log of base 10 RL. I hope I'm not saying anything incorrect so far, because sometimes to say some of these things it can trick you. So yes, so we have this now. So I'm seeing log of base 10 here, so and log of base 10 here. These two things are common on both sides, so I could simply go ahead and cancel them out. So at the end of the day, RL is equal to R naught I to the minus 1. Or in some cases, you could see us write it as this to say RL is equal to R naught divided by IB, right? Because the laws of indices tells us that we can do that. Okay. So with that being said, right, you could get your 1 mark. You could, I don't know if that really values 1 mark, but that's the equation that they want us to write here. All right. So that's the equation to say RL is equal to um, R naught divided by IB. Now the question continues, ladies and gentlemen. It says that R dark is defined as the resistance of the LDR when the luminous, when the light intensity I is less than or equal to 0.01 lux, or lux rather, one of them. It says here, determine the threshold value of R dark using the equation derived in CII. So you see, one of the tricky things is that, they from time to time they link the questions together. So if you never get the first part correct, then the next part obviously you're not get it correct if you get it incorrect. So you have to make sure you get the things them correct, so that when you move on to the next question, it don't affect the price or right or affect your answer. So with that being said, R dark is what they call the resistance of the LDR. So the equation that we just came up with a while ago. As a matter of fact, let's see here, right? So the equation that we came up with a while ago, that said RL. So R dark is technically RL because that is basically the resistance of the LDR. And we know that RL is the resistance of the LDR basically. R naught, right, divided by IB, right? So one of the things they told us is that I is less than or equal to 0.01 lux. Now, so with that being said, technically they're saying that I is equal to 0.01 lux. So with that being said, just a while ago we used the graph to find the value for I naught, right? I naught was corresponding to be, R naught was corresponding to be 10 to the fifth, ohms. So, and we also found from the graph that B, right, is equal to 1. So all we need to do now is to just put things in the equation to find out what R dark or RL is equal to. So 10 to the fifth power divided by I, in this case 0.01 raised to the power of 1, right? Once you do that and work that out, you will get a value to say that RL, which is basically R dark, is equal to 10 to the fifth ohms. And your units in this case is very important. If you leave out the units, I suppose that you might still get the marks, but please don't leave out the units, right? That is what separates between a 1 and a 2. So please don't leave it out. Now it says using the graph in figure 4 on page whatever, it says determine the threshold value for R dark, right? So because they told us the intensity, right, which is technically 0.01 lux, what they now want us to do is to find out the R dark value that corresponds to that intensity, right? So what we need to do now is to look at the equation that talks about intensity. So we know the equation, well, not the equation, but the part of the equation that talks about intensity has to do with the x value, and that is log of base 10 I, right? So basically this is equal to 0.01. So what we want to do is to find out, let me do that again. So what I would do in this case is say log of base 10 times 0.01. I believe that's what I would have to do here to find out um, the log value basically. So let me just erase this part here, right? So let's see, right? Yeah, so log of I, since I is equal to zero point zero 0.01, we now need to find log of that value, right? So let's go ahead. Log of 0.01, we get negative 2, right? So technically, on the graph, which we're going to look at now, we need to find where negative 2 is on the x-axis, right? So pretty much my graph here, I didn't, you know, copy it properly or something of that nature. I cut it off a little bit. I never knew I needed that part. But you would read the value. So you would find negative 2. Once you find negative 2, you go all the way up, right? Once you go all the way up, you're going to now extrapolate the graph. This is what we call extrapolation by just using some broken lines. Go all the way up there, so. And wherever the point would meet, then that will tell you what the not it won't tell you what RL is equal to exactly, but it's going to give you a value. Um, Let me just pause the video and fix this so that you can see what I'm talking about. All right. So here we are now. So we know that the intensity, would give us that negative 2 value there. So all we now need to do is to go all the way up on the graph here, right? We're going to extrapolate the graph, meaning that we're going to make it continue all the way up. And I still believe that I never get it correct at the same time. I needed some more space based on what this is saying here, right? Let me just fix that quickly, right? Let me just fix that quickly, so that you guys can see what we're talking about here. Right? So you want to extrapolate the graph using broken lines all the way up there, you know. So it would correspond to this point. Now when you find that value is telling us that log of base 10 RL is equal to 7. Now they want you to find RL. They want you to see if RL, you know, matches up to the value that they previously showed you, right? Because we would have calculated RL a while ago, you know. And I believe we got 10 to the 7th. So they want to see now if it makes sense to us. So technically, we're saying finding the antilog of 7, which is saying, the exponent raised to the power of 7, which is technically exactly what was previously determined by. Did we find anything about? I think. Let me see. Yes, so it's basically the same thing, right? It's basically the same thing. So RL is 10 to the 7 ohms. All right. Having said all of that, just a while ago now, so we would have confirmed that RL, right? RL is equal to let me see here. So they want us to confirm to determine the value of I, the intensity being measured. So a while ago, we would have found out that RL is 10 to the 7 ohms. Now, you remember the whole Wheatstone bridge equation that you guys would have to derive in that thing that says, RL is equal to, then you have to go back and look, I don't remember, right? But you would have come to this point, so this is what, R1 upon R2, right? So we're going to use this, you see? We're going to use this to assist us here. So we're going to work out and find the RL value. When we find the RL value now, we're going to match it up back to the graph. I mean, it's a lot of work, you know. It's a lot of work. It's 4 marks, by the way. 4 marks, right? But I think the equation that we derived, that's what we're going to use, right? We're going to use that equation. Remember that equation that we derived a while ago that says RL is equal to R naught divided by IB. That is what we're going to use here to ascertain that value for I. So yeah, basically. So we'll go ahead and find RL using all that information. So R1 is 2.2 kilo divided by 4.7 kilo times 3,350 ohms, right? Kilo and kilo would cancel out, right? So if you do when you do the math, you're supposed to get a value to say that RL is equal to 1,568 ohms, all right? Now once we have that, then to find that I value, we're going to transpose to make I become the subject. So once we do that, I is equal to R naught. By the way, it's IB. So let's make IB become the subject. So IB is equal to R naught divided by RL. We would have initially found out what B is. B was 1, right? And we found out what R naught was. That was 10 to the 5. So all we're now doing here is just simply putting in that information, right? So now we have it to say that 10 to the 5th, right, divided by 1,568. Once you do that, then you would simply find out the value for for I, the intensity. So in this case, you should get a value of intensity of 63.8 lux, right? So that is what is being asked here. I mean, it's a lot. I can tell you that. It's a whole lot. Trust me. But prepare for it, guys. Prepare for something crazy, for something weird. I mean, escape, obviously. Now, we move on now, talking about the same question, the whole Wheatstone bridge question. It says, explain why is it desirable to make VB, the supply to the Wheatstone bridge, as small as practicable or something of that nature, right? So in this case, one of the things you have to understand, ladies and gentlemen, right, is that the less voltage you have flowing, right, or not say flowing, but the less voltage across a component, it means that less current will be required, because what you must understand, the voltage and charge are tied together, right? Voltage and charge, they are tied together. So if you have a very high voltage, what that means, it will cause a very large current, because the higher the potential, it means that more work is going to be done to move a charge. Because if you remember the definition for potential difference is the work done per unit charge. So basically, if you have more voltage, it means that you're going to require more work. When you require more work, it means that you're going to generate more heat. And what you don't want to generate a lot of heat when you're using those resistors in the Wheatstone bridge. Because if you create more heat, more heat is going to ultimately result in a higher resistance. So that resistance will affect the operation of the Wheatstone bridge. So let me see if it makes sense to you guys now. So one of the first thing you must understand is that if you have a very high voltage across those resistors within the Wheatstone bridge, right? It simply means that there's gonna obviously there's gonna be a need for a much higher current, right? Because of the fact that the potential difference is much higher. With that being said, having a much higher current, right, flowing through the resistors is going to create a lot more heating effect, right? And with that being said, that will do several things. One, it is going to affect the resistance of the wires, right? And of course, it will create some amount of damage to the LDR as well. Because I mean, if you have high large current flowing through any resistor, it's going to, obviously impact on the effectiveness of the resistor, right? So that's a thing there that we must understand. So it is said here that it is recommended to keep the current value as small as possible, right? So that it can allow for uh, the Wheatstone bridge to accurately, measure what it is supposed to measure and all of that kind of stuff, right? So I hope that makes sense to you. Now, it says here, state one example of a practical application of an LDR and briefly describe its operation. So one of the practical thing here is when we're dealing with a light bulb. No, not a light bulb, but a street light rather. Street light, right? Now, how this works, right? I mean, you know, so the LDR of course is that obviously that transducer that will react to light. But when how the LDR works in the street light, it's almost like a reverse technology in a sense because what 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 you would expect to happen is not what is actually happening. Meaning that you expect that the light would turn on when there's more light shining on the LDR. But that is not what happens. But what simply happens is that, yes, you need the LDR, right? So when light is shining on the LDR, right, there is another resistor here. So let's imagine it says here that when light is shining on the LDR, right, the resistance is going to decrease. The resistance is going to decrease. So, but look at it now. The street light only turn on during the night. So during the night, what you would realize is that the resistance here is going to be much higher. Now that is now going to cause a different voltage to be dropped across this resistor that is basically in series with. So this is almost like a potential divider formula, so to speak. So your LDR would be here. LDR would be here, right? In the night, no light is shining on it, so it means that the resistance is going to increase. When that resistance increase, it's now going to create a less voltage drop across this resistor, and chances are it could have then been connected to a operational amplifier, which could now give us a particular signal, right, to tell us when to turn on the thing, basically, depending on the voltage, because you know that operational amplifier works off of voltages and all of that kind of thing, right? So that in itself would somewhat explain how it is working, right? So that would somewhat explain that. Um, so let me see here. It says, "Are any statement that shows that the LDR will trigger a change in." Yeah. So as we said now, um, as night comes on, less light is shining on the LDR, right? Thus creating a much higher resistance. That higher resistance is going to require a more voltage across that LDR. The voltage across the regular resistor in this circuit will vary, thus somewhat creating a trigger in another part of a circuit to cause the street light to turn on basically, right? So the way how we expect it to work is not the way how it actually works, right? So that's why whenever you're creating circuits and all that, you have to have other parts or other components involved in the whole operation, so to speak. It's a two-mark question. I mean, you can definitely read up some more about this. I don't know how best my explanation was to explain it to you, but there are several ways we could take this thing, right? But one of the main things you must understand is that as the intensity of light changes, right, then it affects the resistance of the LDR, which could possibly trigger, you know, something else in the circuit to operate, right? Uh, and of course, you know, giving some type of I would say response. So there's a circuit we call a comparator circuit, and a comparator circuit, right, is one that compares the voltage. So that would be a primary example of how this thing could actually work, But I mean, I don't think it might require for you to be stating all of this, but you know, um, so it could be a case that the circuit is designed in such a way to give you, um, it will say to you that if the voltage is 10 for argument's sake, then it's gonna now tell the the um the light to turn on, that kind of stuff, right? So depending on the polarity that comes here, right? Depending on the polarity that comes here, you might have seen something like this before. What this is technically doing is comparing the voltages. So this is kind of like the easiest circuit that I could think about mainly right now. That so this is what is an operational amplifier, right? Um, so this is your LDR, right? So based on this, so from time to time, depending on the intensity of the light, your resistance here is going to change, which is going to affect the voltage across um, this particular resistor, which will now determine and tell you what voltage will go towards um, this operational amplifier. How the comparator works, the comparator says that if this voltage is higher than this voltage, so imagine that this is 5 and this is 4, then it's going to favor the voltage that has the higher value. So it means that the voltage here um, will, or in essence, the voltage that the operational amplifier will take is the negative, is the voltage that is at the negative terminal. Now, we must remember how the operational amplifier, well, we must remember how the operational, well, not the operational amplifier, but we must remember how an LDR works, right? I believe this is the positive end of the diode, I should say, or an LED, right? And this is the negative part. At this point in time, the the LED will not turn on because of negative and positive, right? The only time it will turn on is if this voltage is higher than this voltage. So positive to positive, that is when the diode will be in forward bias. But that's a whole not a kettle of fish, right? So we leave that as that. Now, basically, we're finished with this aspect of the paper for now. I mean, the other part of the question is not related to what is really coming on the exam, so we won't go through that. But what I'm going to do next is go straight into talking about photoelectric effect. Let me just see how much minutes I have on this. All right, so it's 40 minutes. I can do some more, right? Photoelectric effect. See that is coming on the exam. Might as well we just talk about that as well. Now, ladies and gentlemen, photoelectric effect is a very I like photoelectric effect to a certain degree because it can't get more complicated than how it seems, right? When we talk about the photoelectric effect, we must recall the classical wave theory, right? We should recall that, please. So just gain a better insight as to what took place back then and the arguments against the classical wave theory, because they could ask you questions about that. I mean, you should be able to can talk about the photoelectric effect. So simply put, I mean, photoelectric effect is just that whole theory, or yeah, that depicts or explains that light has a particulate nature, so to speak. So it is not only a wave. Light is not only a wave, but scientists such as Planck and Planck and a man like Einstein found out that light is not just simply a a wave, but it has particular properties, right? And with all of this that we're talking about here, we must also understand that in just the same way light is considered to be a particle is also considered to be, or is considered to have wave-like properties. And one experiment that you can look back on is the Huygens, I think it's the Huygens or Huygens, experiment, right? Or another one we can look at is the wave duality, scenario there, right? So that is something to when you fire an electron, that electron going through a slit will now be able to give you diffraction patterns and all that. So those things come under this. So you should go through that. It says, see the name of the scientist who is credited with the explanation of the photoelectric effect. There are several scientists that did work as it relates to it, right? But Einstein, right, is the man who is credited for this more than anybody else, right? So Einstein found out a lot of things. So it says, with reference to the photoelectric effect, right? Explain what is meant by the threshold frequency. So simply put, the threshold frequency is the minimum frequency at which photo emissions take place. All right. Remember now, ladies and gentlemen, that if I have a piece of metal, right, and I shine light on it, right, not every wavelength or not every frequency of light will allow photo emission to take place. The only time photo emission will take place is if the wave has a particular frequency or a minimum frequency that will have enough energy to liberate the electrons from the metal surface, or in other words, to break the electrons from their force of attraction. All right. So that is simply what the threshold frequency is, and we know the symbol for that is F naught. Work function. No, ladies and gentlemen, the work function and the threshold frequency, it comes hand in hand, right? So just now we'll talk about the minimum frequency, right, of light, that is of the incident radiation that is required to cause photo emission. Now, when it comes on to the work function, simply put, is the energy that is required from the incident radiation to completely remove an electron from the metal surface. And with that being said, we have an equation here, so we could define the work function in terms of its symbols as W, or we use psi. So psi is equal to Planck's constant times F naught, right? Where H is Planck's constant, which is always given to you guys. I believe it's 6.63 times 10 to the minus 34 joules second. And of course, threshold frequency is measured in hertz. All right. So in this explanation about the work function, to get a little bit more marks, not to, or to get your full marks, you just write the equation as well. All right. Because I mean, it doesn't kill you to write the equation, right? This is typically what happens whenever we're trying to, uh, deal with this whole photoelectric effect scenario. You would generally have what we call a vacuum chamber. The reason for a vacuum chamber is obviously because you don't want the electrons to be interfering with anything as it moves through the from one plate to the next plate, right? So they call it an evacuated quartz tube, but we could call it an evacuated tube, right? I mean, there's a voltage that is applied to it, right? So as you can see, positive to positive here, right? It's going to cause some level of repulsion, I believe. But either way, we don't want to talk much about that right now. But what we want to do here is to just fill out the table. So you get a 1 mark to fill out the table, right? So what they want here is to find the frequency. Because we're dealing with light, ladies and gentlemen. The speed of light, as we can imagine, is 3 times 10 to the 8 meters per second. See? And from there's an equation because we're dealing with speed of light and we're dealing with waves. This equation comes in handy to say wavelength times frequency is equal to the speed of light. If I want to find the frequency now, all I need to do is to just transpose this equation to make frequency become the subject. Speed of light is 3 times 10 to the 8 divided by the wavelength. So in this case, the wavelength here is 594, but not just 594, 594 nanometers. All right. So please, I'm asking you guys, once you get that table, you see, look in the table for me, please. Because right now, as you can see, the frequency is times 10 to the 14th. So with that being said, if you don't follow the table, you can make mistakes, right? Please, so let's try not to make any mistakes or leave out any information, because if you go ahead and write this, right, and not incorporate the times 10 to the minus 9, then the answer go wrong, and it's a 1 mark thing. You don't want to lose 1 mark. So let's just quickly just fill out these. I mean, I think you guys could do the rest, right? But the thing is, I believe they want us to photograph, so we might have to complete it. Oh, this is 94. That was the first one. This is 94. So this value right here that we're looking on is 5.05. No, there's no need for you to go back and write times 10 to the 14th, all right? Because times 10 to the 14th is already in the table. So you don't need to go back and write that, all right? Because that would be redundant, and that technically could tell you that you're saying 5.05 times 10 to the 14 times 10 to the 14, which is technically not correct. So let's just finish up this quickly. You want to score as much marks as you can. All right, so that just completes the table there. It says on the graph you provided, it says photograph of stopping potential energy, right, versus the frequency of the metal. This can be a little bit tricky because they're saying stopping potential energy, right? You're not saying stopping potential, but stopping potential energy. Now, if we're saying stopping potential energy, technically they're saying that this is equal to EVS, right? That's my take from this question, right? Because EVS is really talking about the stopping potential energy. That's what I mean. So we have to now go over here and practically uh times all of these right here by times 10 to the well 1.6 times 10 to the 10 to the minus 19. All of these have to be times 10 to the 1.6 times 10 to the minus 19, right? And the whole reason for that is because of the fact that they say stopping potential energy. If they had just said stopping potential, then you would use VS. But that is not what they're asking us to do. And what I must point out here as well is that your stopping potential energy, right? Energy is technically equal to the maximum kinetic energy of the electron, right? So whatsoever energy that was used to stop the electron, right? That energy will correspond to the maximum potential energy, maximum kinetic energy that the electron has. So let me say that again. So chances are, whenever you're doing this experiment, the aim is to stop the electron, right? I don't know if you guys did that simulation in any of your classes when you did it, but the aim right here is to stop the electron before it reaches the negative plate, right? So you want to have a particular voltage that will stop the electron from reaching the plate. If I can stop this electron using some amount of energy, that energy is essentially the energy that the electron would have had initially, which is basically the kinetic energy, right? So that is what is happening here. So I mean, you guys will have to. I want to plot this graph. Just give me a second to just pause it and plot it because it's going to take about a time.